Close your eyes for a moment. Imagine you are standing somewhere completely still. There is no sound, no wind, no hum of a city or rustling of leaves. Only silence. The kind of silence that feels ancient, as if the universe itself is holding its breath. Now, open your eyes. Above you, the sky is not black. It is not the quiet darkness you know. It burns, a slow, molten amber, as if the entire atmosphere is on fire. The clouds are not made of water. They drift in long, slow spirals of sulfur and vaporized rock. And the ground beneath your feet, it does not hold still. It breathes, it shifts, it glows. Because what you are standing on is not solid earth. It is a crust of hardened lava, thin as ice over a frozen lake. And beneath it, an ocean, not of water, but of molten stone, stretching thousands of kilometers in every direction, boiling gently at temperatures that would reduce any metal on Earth to vapor within seconds. You are not on Earth. You are standing on a world that should not exist. And yet, it does, orbiting a star so close that a single year there lasts fewer than 20 hours. A world where the rocks themselves melt and rain back down from the sky. A world that, for all its impossible violence, has been quietly spinning in the darkness of the cosmos for billions of years. And this is only the beginning, because somewhere out there, beyond the reach of every telescope, beyond the edge of what we have yet mapped, there are worlds covered entirely by oceans hundreds of kilometers deep, with no seafloor, no islands, no shore. Worlds where the clouds are made of iron particles that rain upward. Worlds where the sky is so thick with methane that the sunsets last for days. Worlds that spin so slowly they keep one face forever bathed in scalding light, and the other locked in eternal planet-wide night. And then, and this is the part that changes everything, there are worlds that look almost familiar. Worlds where liquid water may pool in quiet valleys, where temperatures settle into something livable, where the chemistry of life, carbon, hydrogen, oxygen, nitrogen, drifts through the atmosphere in the same proportions that made Earth a cradle for everything you have ever known. We have found them, thousands of them. They are called exoplanets, worlds orbiting other stars, beyond our sun. And in the last 3 decades, humanity has gone from wondering if any such worlds existed at all, to cataloging a universe so full of planets that scientists now believe there may be more worlds in the cosmos than there are. Grains of sand on every beach on Earth. But here is what makes all of this so extraordinary. We cannot visit them. Not yet. Most of these worlds are so far away that even traveling at the speed of light, the fastest anything in the universe can move, reaching the nearest ones would take years. Reaching the strangest ones would take lifetimes, centuries, millennia. And yet, we see them. With instruments of almost impossible sensitivity, we have detected the way these worlds tug on their stars. We have watched their shadows pass across distant suns and measured the chemical fingerprints of their atmospheres. We have heard, in the data, the whisper of weather systems, volcanic activity, and the slow dance of moons we have never directly seen. We are standing at the edge of the greatest exploration in human history, not across an ocean or a continent, but across the cosmos itself. And tonight, we are going to explore, we're going to cross light years together, quietly, with open eyes and open minds. We will visit the strangest, most beautiful, most bewildering worlds ever discovered. We will stand on oceans of lava and beneath skies of evaporating iron. We will hover at the edge of gas giants, so enormous they make Jupiter look small. And we will drift slowly toward worlds where, just maybe, something is looking back. This is not a lecture. This is not a list of facts. This is a journey, a quiet, unhurried journey through the most astonishing places the universe has ever made. And it begins with a single question, one that scientists have been asking since the first exoplanet was confirmed in the early 1990s, and one that still does not have a complete answer today. Are we alone? Settle in. Take a slow breath. Let the noise of the world fall away. The stars are waiting. Before we travel anywhere, let us be honest about something. The universe is not a comfortable place. The vast majority of it is empty. A cold, dark vacuum where nothing lives and nothing moves. The stars themselves are violent furnaces. Planets are often airless rocks, or crushing balls of gas, or frozen wastelands so cold that even the most resilient life we know of on Earth would not survive a single second. And yet, something extraordinary happened here. On a small, pale blue world orbiting an unremarkable star in the outer arm of a galaxy containing 400 billion other stars, life appeared. Not just microbial life clinging to the edges of survivability, life that eventually grew complex enough to look up at the sky and ask the most important question a mind has ever formed. Is there anyone else? What you are about to discover in this journey is that the universe, for all its emptiness and violence, is also staggeringly generous with the ingredients needed to answer yes. In the hours ahead, we're going to explore 10 categories of worlds that have either been discovered, confirmed by data, or theorized by the most serious planetary scientists alive today. Each one is real. Each one is strange. And each one will challenge something you thought you understood about what a planet can be. We will begin with the most extreme environments known, the lava worlds that hug their stars so tightly they are perpetually melting. These are not fictional places from science fiction films. They are real planets with names and coordinates, orbiting stars you could point to in the night sky. We will explore what makes them so strange, and, perhaps most surprisingly, why some scientists believe they deserve attention not despite their violence, but because of it. From there, we will travel outward to ocean worlds that may hold more liquid water in a single planet than all of Earth's oceans combined, but where the water is so deep, so pressurized, that it transforms into exotic forms of ice that exist at the bottom of planetary seas hundreds of kilometers below the surface. We will visit worlds where the skies are the color of bruised copper, where it rains glass sideways, where the wind moves faster than the rotation of the planet itself. We will explore super-Earths, planets larger than our own, but with surfaces that may still be solid, still temperate, still covered in the quiet geography of valleys and plains. And then, near the end of our journey, we will arrive at the worlds that feel closest to home, the ones in what scientists call the Goldilocks zone, not too hot, not too cold, where liquid water could persist on a surface, where atmospheres might breathe the chemistry we recognize. But here is the promise that makes this journey more than a tour of extreme environments. Every single world we visit is going to raise a new question that we cannot yet answer. That is not a limitation. That is the beauty of this moment in history. We are living in the first era of exoplanet science. 30 years ago, we had 0 confirmed planets beyond our solar system. Today, we have over 5,000 confirmed, with tens of thousands more candidates waiting for verification. And the James Webb Space Telescope, the most powerful observatory ever built, has only been operational for a short time, and it is already transforming what we thought we knew. Every answer it finds opens a door that leads to 3 more mysteries. That is what this journey is really about. Not answers, not certainty, but the slow, breathtaking process of a species waking up to the scale of the universe it inhabits, and realizing, for the first time with real evidence in hand, that the cosmos is not empty. It is full of worlds. They are alien and beautiful and strange. They are nothing like what we expected. And some of them, just some, might not be so different from the one you are sitting on right now. Take a moment. The universe is very large. We are very small. But we are looking, and in that looking, something remarkable is happening. Let us begin. The first world we visit has a name that sounds almost bureaucratic for something so extraordinary. 55 Cancri E. It orbits a star called 55 Cancri, which is visible, just barely, to the naked eye on a clear night, sitting in the constellation Cancer. If you know where to look, you can see the star itself, but you would never guess, looking at that faint point of light, that one of its planets is a world where the surface glows. Not metaphorically, literally glows. 55 Cancri E is what scientists classify as an ultra-hot rocky planet, or more colloquially, a lava world. It completes a full orbit around its star in just 17.7 hours. To put that in perspective, Earth takes 365 days to complete one orbit. This world completes its year while you sleep. Because it orbits so close to its star, the temperatures on its day-side surface reach approximately 2,400 degrees Celsius. That is, hot enough to melt iron, hot enough to vaporize most rock, hot enough that the surface itself, the actual crust of the planet, is in a perpetual state of melting, cooling, and remelting. But that was not the strangest part. When scientists first examined 55 Cancri E using the Spitzer Space Telescope, they expected the temperature readings to show something simple: a scorching hot day side and a cold, dark night side. That is what basic physics predicts for a planet this close to its star, especially one that is likely tidally locked, meaning one face always points toward the sun, and the other always faces away, never rotating. What they found instead broke the models. The heat was not where it should have been. Instead of the hottest point being directly under the star, which is where you would logically expect an unmoving, tidally locked surface to be hottest, the heat was shifted, offset, as if something was moving it, redistributing it. The leading hypothesis? 55 Cancri may have an atmosphere, not one made of oxygen and nitrogen, like Earth's, not one made of carbon dioxide like Venus, but one made of vaporized rock. Think about that for a moment. An atmosphere of rock. On the day side of this world, the temperatures are so extreme that rock itself evaporates. It turns from solid or liquid into gas, drifting upward into the sky. This rock vapor atmosphere then flows across the planet, carried by winds that move at supersonic speeds, before cooling and raining back down on the night side as rock. Rock rain. Not metaphorical rock rain. Actual droplets of mineral condensate falling silently back to the surface on the dark side of a planet that never rotates, never breathes, never stops cycling its own substance through an atmosphere made of itself. And yet, scientists are not sure this model is correct. Subsequent observations have shown that the temperature of 55 Cancri fluctuates over time, changing from measurement to measurement in ways that an atmosphere of vaporized rock alone cannot easily explain. Some researchers have proposed that the planet may actually have a more complex geological surface, perhaps covered not in a static ocean of magma, but in a dynamic system of volcanic activity, eruptions, lava flows, surface cycling, that creates a changing thermal signature. In 2023, the James Webb Space Telescope turned its instruments toward 55 Cancri and captured something remarkable. It detected clear evidence of a volatile atmosphere, one containing carbon dioxide or carbon monoxide or both, suggesting that this world is not just a hot rock, but something far more geologically and atmospherically active than previously imagined. The answer raised an even bigger question. If 55 Cancri has a carbon-bearing atmosphere despite its surface temperatures, where did that carbon come from? Was it always there? Did it outgas from the interior through volcanic activity? Is it being continuously replenished? And if it is, what does that mean for the stability of the planet's surface chemistry over geological time? We do not yet know, but 55 Cancri is not alone. Across the galaxy, we have found dozens of worlds in this category. Ultra-short period planets hugging their stars so tightly that their surfaces exist in permanent geological crisis. TOI 1685b, WAS P47e, K2141b. Each one is a variation on the same terrifying theme. A rocky world caught in the gravitational embrace of a star so close that the planet cannot simply cool and solidify into the quiet. Geology we see on Earth. K2141b is perhaps the most extreme example. It orbits its star so closely, completing a full orbit in just 6.7 hours, that the gravitational forces are beginning to stretch the planet into a slightly elongated shape. Its dayside surface is estimated to exceed 3,000 degrees Celsius, hot enough that even the mineral olivine, one of the most heat-resistant common minerals, would boil away into vapor. On K2, 141b's dayside, the oceans are not water. They are magma, shallow seas of molten rock, stirred by convection from the even hotter rock below. And above these magma seas, the atmosphere carries vaporized sodium and silicon and oxygen in a swirling, superheated haze. Scientists believe that winds on K2, 141b's dayside carry this rock vapor atmosphere toward the cold night side at speeds exceeding 5,000 kilometers per hour. As it crosses the terminator, the boundary between permanent day and permanent night, it cools and falls as a kind of mineral snow, building up strange geological formations on the dark hemisphere that will eventually slide or flow back toward the day side as a slow, viscous lava tide. This planet has a rock cycle, not the rock cycle you learned in school. The slow, millions of years process by which Earth's crust subducts and reforms. A rock cycle measured in hours, a constant, planetary-scale conveyor belt of mineral evaporation, atmospheric transport, precipitation, and melt. It is simultaneously one of the most alien and one of the most geologically understandable things in the cosmos. The process is familiar. The scale and the extremity are not. And here is what makes lava worlds so interesting to scientists who are thinking carefully about life and habitability. Not because lava worlds themselves could harbor life. They almost certainly could not, but because they represent a class of planets that are geologically very active, and geological activity, volcanism, outgassing, mineral cycling, is thought to be one of the key ingredients in generating the atmospheric chemistry that a living world needs. Earth's own atmosphere is thought to have been shaped, in large part, by volcanic outgassing over billions of years. The carbon dioxide, water vapor, nitrogen, and other compounds that volcanoes release have profoundly influenced the conditions that made life possible here. So when scientists look at lava worlds and see evidence of vigorous outgassing, rock vapor atmospheres, carbon-rich compounds, dynamic surface cycling, they are not seeing alien hellscapes so much as they are seeing, in extreme form, one of the processes that may have been essential to the origin of life on Earth. The very violence of these worlds may be, in a strange sense, a kind of fertility. Yet another mystery emerged from this line of thinking. If lava worlds represent an early, extreme phase of rocky planet evolution, and some researchers believe they do, seeing them as planets that formed close to their stars before the disk of gas and rock around the young star dispersed, then some of them may eventually calm down. Their geological activity may slow. Their surface may solidify. Their volatile inventory may change. In other words, some lava worlds may be on their way to becoming something else, something quieter, something perhaps more familiar. We do not know if any lava world has ever made that transition. We do not know if the timescales involved are possible within the lifetime of the host star. But the possibility is there, humming quietly beneath the surface of the data, like magma beneath a cooling crust. And that is enough to keep looking. Now imagine the opposite. Not fire, Water. But not the water you know. Not the shallow, sun-warmed oceans of Earth, where the average depth is only about 3.7 kilometers. And sunlight penetrates the top few hundred meters, driving the entire food web of the sea. Not that water. Imagine an ocean so deep that no bottom exists in any meaningful sense. An ocean that begins at the surface of a planet and extends downward for hundreds of kilometers, pressing down with a weight so immense that the water at the very base is no longer liquid or ice in any conventional sense. It becomes something called Ice 7, or supersonic ice, a bizarre state of matter in which the oxygen atoms lock into a crystalline lattice, while the hydrogen atoms move freely through it, like liquid in a solid cage. This is what scientists call an ocean world, and we believe they may be among the most common types of planets in the galaxy. The concept gained enormous traction in our own solar system, long before we began studying exoplanets in detail. Europa, one of Jupiter's moons, harbors a liquid water ocean beneath its icy shell that contains roughly twice the volume of all Earth's oceans combined. Enceladus, a moon of Saturn, erupts plumes of water vapor and organic molecules from its south pole, hinting at a warm, chemically rich sea below. Titan, also orbiting Saturn, has lakes and rivers and rain, not of water, but of liquid methane and ethane in an eerie liquid cycle that mirrors Earth's hydrological cycle with a different chemistry. These are not exoplanets. They are moons. But they taught us something crucial. Liquid water can exist in places we never expected. In the dark, in the cold, far from the warmth of the sun, water persists, sustained by tidal heating, radiogenic decay, or the insulating blanket of ice above. So when we began surveying exoplanets for planets larger than Earth, what scientists call sub-Neptunes and super-Earths, one category kept appearing with surprising frequency. Planets with densities that fell between a rocky planet like Earth and a gas-rich planet like Neptune, in a range that suggested they might be composed largely of water. These became known as water worlds, or ocean worlds, and one of the most studied is a planet called GJ1214b. GJ1214b orbits a small red dwarf star about 40 light-years from Earth. It was discovered in 2009 and immediately attracted enormous attention because of its unusual properties. It is about 2.7 times the size of Earth and about 6.5 times more massive, but its density falls squarely in the range that suggests a world with a thick layer of water, ice, or both. When the Hubble Space Telescope attempted to characterize its atmosphere, something strange happened. The atmosphere was completely featureless, or rather, it appeared to have a high-altitude layer of clouds or haze that obscured any chemical signatures below. No matter what wavelength of light scientists used to probe it, the planet's atmosphere stubbornly refused to reveal its secrets. For over a decade, GJ1214b remained one of the most tantalizing and frustrating mysteries in exoplanet science. Then, in 2023, the James Webb Space Telescope looked at it, and the results were, in their own quiet way, extraordinary. Webb detected clear signatures in the atmosphere of GJ1214b, but not hydrogen, not the light, puffy atmosphere of a gas-rich world. Instead, The data pointed toward a much heavier atmosphere, consistent with water vapor, carbon dioxide, and possibly methane. A thick, dense atmosphere of heavy molecules, blanketing a world that, beneath those clouds, may be covered in a global ocean stretching from pole to pole, with no land, no shore, no depth that sunlight ever reaches. But this is where the story becomes genuinely strange. The water on GJ 1214b, if the water world hypothesis is correct, would not behave like water on Earth. Under pressures of millions of atmospheres, compressing thousands of kilometers of liquid above, the water at the base of the ocean would transition into those exotic high-pressure ice phases. Not cold ice, not the ice you find in a glass of water, but hot ice. Water so compressed that it solidifies despite temperatures that might exceed hundreds of degrees Celsius. Hot ice under an ocean of crushing water, at the center of a planet covered entirely in sea. Scientists soon discovered that this is not unique to GJ 1214b. A planet called Kepler 62f, orbiting a star about 1,200 light-years away, may also be an ocean world. TOI 1452b, discovered in 2022, and orbiting a red dwarf about 100 light-years from Earth, has been described by its discoverers as one of the best candidates for an ocean world ever found. Its radius and mass suggest that as much as 30% of its total mass could be water, compared to less than 1/10 of 1% for Earth. This is an ocean not of kilometers, but of thousands of kilometers. And yet, another mystery emerged from these discoveries, one that keeps planetary scientists up at night. If these worlds are entirely covered in global oceans, with no exposed land, no rock-water interface at the surface, no continental shelves or volcanic ridges rising through shallow water, what happens to the chemistry of life? On Earth, some of the most important chemistry for living organisms happens at the interface between rock and water. Hydrothermal vents on the ocean floor provide heat and minerals. Rivers carry dissolved rock minerals from continents into the sea. Shallow coastal zones where sunlight reaches the seafloor are extraordinarily productive ecosystems. On a true ocean world, thousands of kilometers deep, with no shore, all of this is different. The rock-water interface is buried under such immense pressure that it may produce exotic mineral forms that biology, as we know it, cannot easily use. Sunlight penetrates only the top 100 meters or so of an ocean, and if the planet's orbit puts it far enough from its star, even that thin sunlit layer may not receive enough energy to drive photosynthesis as we understand it. Does this mean ocean worlds cannot support life? Not necessarily. Tidal heating, radiogenic decay from radioactive elements in the rocky core, hydrothermal activity at the extreme base of the ocean. These could potentially provide energy for chemosynthetic life, organisms that derive energy from chemical reactions rather than light. But the fundamental architecture of life on such a world, if it exists, would be profoundly different from anything on Earth. And here is the thought that settles in quietly. The more you contemplate these worlds, Earth is sometimes called a water world by scientists who study planetary habitability, and in a sense it is. Water covers 71% of our surface, but compared to GJ 1214b, or TOI 1452b, Earth's oceans are a thin film, a coat of moisture on an essentially rocky planet. The true ocean worlds are something else entirely. They are planets where water is not an accessory to the geology, but the dominant fact of existence, where the entire physical and chemical environment is defined by water, from the cloud tops to the strange, hot, crystalline depths. They are water all the way down. And somewhere in those unimaginable depths, in some warm current, warmed by the heat of a rocky core pressing up through thousands of kilometers of pressure ice and ocean, the chemistry that leads to life may be doing what chemistry does, slowly, in the dark, assembling itself. We do not know. But the question that lingers, drifting like a current in a deep, lightless sea, is this: if life emerged in Earth's ocean, an ocean that is, by cosmic standards, almost vanishingly thin, what might emerge in an ocean that covers an entire world and goes thousands of kilometers down? For most of human history, when astronomers thought about what planetary systems looked like, they assumed they looked something like ours. Small, rocky planets close to the star. Large, gaseous planets far away, where it is cold enough for the lighter molecules, hydrogen, helium, methane, ammonia, to remain in gaseous form and accumulate into enormous spheres. This was the model. It made sense. It was backed by the physics of how planets form. The so-called snow line in a protoplanetary disk, beyond which icy and gaseous material can accumulate efficiently. And then, in 1995, everything changed. Astronomers Michel Mayor and Didier Queloz discovered a planet orbiting the star 51 Pegasi, a star in the constellation Pegasus, about 50 light-years from Earth. They named the planet 51 Pegasi b, and what they found was, by the standards of every model that existed at the time, completely impossible. It was a gas giant, roughly half the mass of Jupiter, possibly larger. But instead of orbiting at a comfortable distance, like Jupiter, sitting at 5.2 astronomical units from the Sun, it was orbiting at 0.052 astronomical units from its star. It was 8 times closer to 51 Pegasi than Mercury is to our Sun. It completed one orbit in 4.23 days. The planet was not just warm, it was, as subsequent measurements confirmed, blisteringly hot, with temperatures on its dayside exceeding 1,000 degrees Celsius, and in more extreme cases of this type, reaching 2,500 degrees or beyond. These worlds were immediately dubbed hot Jupiters, and they were everywhere, not literally everywhere. We now know that hot Jupiters are actually a relatively rare type of planet, present around perhaps 1% of Sun-like stars. But when the first radial velocity surveys, the technique that detected 51 Pegasi b began systematically scanning stars for planetary companions. Hot Jupiters dominated the initial findings. They were the easiest to detect. Their large mass created a strong gravitational tug on their star, and their short orbital period meant the signal repeated quickly. The scientific community was initially skeptical. Mayor and Queloz result was challenged, questioned, and tested by other telescopes around the world. But within months, it was confirmed. And then, more hot Jupiters appeared. And more. Something was fundamentally wrong with the models. Scientists soon discovered that the solution to this puzzle was not that the models were completely wrong, but that they were incomplete. Gas giants, it turned out, do not necessarily stay where they form. They migrate. In the early, chaotic era of a planetary system's formation, when the protoplanetary disk of gas and dust is still present, gravitational interactions between a forming gas giant and the disk can cause the planet to spiral inward. The disk acts as a brake, sapping the planet's orbital energy and drawing it closer and closer to the star over millions of years. If the disk disperses before the planet falls into the star, the planet can end up stranded in a tight orbit, a hot Jupiter, forever locked in a relationship with its star it was never supposed to have. But that wasn't the strangest part. As telescopes improved and we began studying hot Jupiters in detail, they turned out to be some of the most bizarre objects in the known universe. Take HD 189-733b. It orbits its star in about 2.2 days, at a distance of roughly 4.4 million kilometers, compared to Earth's 150 million kilometer distance from the Sun. Its atmosphere has been studied in extraordinary detail, and what scientists found there changed how we think about planetary meteorology forever. HD 189-733b's dayside reaches temperatures of around 1,000 degrees Celsius. That alone is remarkable, but it is the planet's wind system that truly defies imagination. Astronomers using the Hubble Space Telescope measured the speed of winds in HD 189-733b's atmosphere at approximately 8,700 kilometers per hour, more than 7 times the speed of sound on Earth. These are not storm-strength winds. These are planetary-scale, hemisphere-crossing gales that circle the entire world, blowing continuously at supersonic speeds, carrying heat from the scalding day side toward the cooler night side. And what is it raining on HD 189-733b? Glass, not raindrops of water, not even the exotic mineral rain of lava worlds. The silicate particles in HD 189-733b's upper atmosphere condense and precipitate as tiny shards of glass, silicate glass, the same basic material as sand. Driven sideways by those 8,700 km/h winds. Glass rain, moving sideways in the dark, on a world where the entire sky is moving faster than any object on Earth's surface has ever moved. Scientists soon discovered that HD 189-733b is not unique in its strangeness. WASP 12b is a hot Jupiter that orbits its star in just 1.09 days, barely over 24 hours. But its most remarkable property is not its speed. It is its shape. The star's gravitational pull is so intense at this distance that it is actively deforming the planet, stretching it into a shape that is slightly elongated in the direction of the star, an egg-like distortion of what would otherwise be a sphere. Even more dramatically, WASP-12b is losing mass. Material from its upper atmosphere is being stripped away by the star's intense radiation and gravity, flowing outward in a stream of gas that spirals back toward the star. WASP-12b is being eaten. Over astronomical timescales, not immediately, not in any human lifetime, but the planet is slowly diminishing, its mass and atmosphere being consumed by the star it orbits too closely. It is, in a very real sense, a dying planet. And then there is WASP-76b. WASP-76b is a hot Jupiter orbiting a star about 640 light-years from Earth. Its day side reaches approximately 2,400 degrees Celsius, hot enough to vaporize iron. And because it is tidally locked, with the same face always pointed toward the star, the day-side iron vapor is carried by powerful winds to the cooler night side, where it condenses and falls as iron rain, actual rain made of iron, falling silently through the atmosphere of a gas giant, on the dark side of a world that never turns to face its sun. The answer raised an even bigger question that scientists have been grappling with ever since. Hot Jupiters should not, by the standard models of planetary formation, have any water in their atmospheres. They form near the snow line or beyond it, where water ice can accumulate. But by the time they migrate inward to their scorching hot orbits, the temperature should be far too high for any water to persist. And yet, several hot Jupiters have been found to have water vapor in their atmospheres. WASP-39b, one of the first exoplanets studied in detail by the James Webb Space Telescope, showed clear and unambiguous evidence of water. Carbon dioxide, sulfur dioxide, and other molecules in its atmosphere, a chemical complexity that was not predicted at those temperatures. Why does WASP-39b have sulfur dioxide? On Earth, sulfur dioxide in the atmosphere is primarily produced by volcanic eruptions and by the reaction of sunlight with sulfur compounds. In 1ASP-39b's atmosphere, scientists believe the source is photochemistry. The same ultraviolet light from the star that destroys some molecules is, paradoxically, also creating new ones through chemical reactions with the sulfur and oxygen already present. A gas giant being irradiated so intensely that its atmosphere is undergoing ongoing chemical synthesis. The universe, it turns out, is a chemist, and it works on scales we are only beginning to comprehend. What happened next surprised researchers working on the long-term fate of hot Jupiters. Some of these planets, it appears, may not survive in their current orbits for the entire lifetime of their star. The same tidal forces that lock them in place are also, very slowly, draining orbital energy from them, drawing them, centimeter by centimeter, orbit by orbit, closer to the stellar surface. WASP-12b is expected to spiral into its star in roughly 3 million years. On cosmic timescales, that is the blink of an eye. These are worlds that are, in a sense, falling in slow motion toward their own destruction. And we are watching. Everything we have explored so far, lava worlds, ocean worlds, hot Jupiters, shares one fundamental characteristic. They orbit a star. They have a sun, however close or distant, that defines their days, their energy budgets, their atmospheric chemistry. But what if a planet had no star? What if, through some gravitational catastrophe in the early life of a planetary system, a world was flung outward, ejected from the family of planets it formed with, cast into the darkness between stars, drifting alone through the galaxy? This is not a hypothetical. It is not science fiction. These worlds exist. They are called free-floating planets, or rogue planets, and they may be among the most numerous type of planet in the galaxy, possibly outnumbering planets in stable stellar orbits. The discovery of rogue planets came in two phases. The first phase was largely theoretical. Simulations of early solar system formation had long suggested that the chaotic gravitational interactions between forming planets could result in ejection events, planets flung into interstellar space by close encounters with larger bodies. Jupiter, in some models of our own solar system's formation, may have ejected several planet-sized objects into the outer solar system or beyond during its early migration. The second phase was observational. Beginning in the early 2000s, surveys of nearby star-forming regions began detecting objects with planetary masses that showed no evidence of orbiting any star. They were simply there, warm, glowing faintly with the residual heat of their formation, floating freely in space. One of the most dramatic discoveries came in 2023, when the James Webb Space Telescope surveyed the Orion Nebula, one of the closest and most active stellar nurseries to Earth, about 1,344 light-years away. And what it found astonished the astronomical community. Webb detected dozens of planet-sized objects in the Orion Nebula that appeared to be orbiting each other. Not a star, but each other. Pairs of planetary mass objects, bound together by their mutual gravity, drifting through the stellar nursery without any parent star. Scientists called them Jupiter Mass Binary Objects, or JUMBOs. The existence of JUMBOs raised an immediate and profound question. How did they form? The two leading possibilities are equally extraordinary. The first is that they formed like stars, from the direct collapse of a small pocket of gas and dust in the nebula, in the same way that a star forms, just without enough mass to ignite nuclear fusion and become a true star. In this model, they are essentially failed stars, or substellar objects, that happened to have masses in the planetary range. The second possibility is that they formed in orbit around a star, as conventional planets, and were then ejected during a dynamical instability in the early planetary system, but remained gravitationally bound to each other, even after the ejection. In this model, they are true planets, just homeless ones, sharing their solitary journey through the galaxy with each other. But that wasn't the strangest part. The strangest part of rogue planets is not their origin. It is what they might be like inside. A planet floating in interstellar space with no star to warm it should be very cold. The surface temperature of a rogue planet, if it has been drifting in space long enough for its formation heat to radiate away, could be around minus 270 degrees Celsius, close to the temperature of the cosmic microwave background, the residual radiation from the Big Bang itself. That sounds like absolute emptiness, a frozen, dead world, with no hope of any chemistry interesting enough to be called geological, let alone biological. But here is what changes everything. Large rogue planets, particularly those in the super-Earth to Neptune mass range, may generate enough internal heat through radiogenic decay of radioactive elements in their rocky cores to maintain temperatures far above their frigid surfaces, deep inside. And some models suggest something even more remarkable. A rogue planet of sufficient size, with a sufficiently thick atmosphere of hydrogen and helium, gases that are extraordinary insulators, could potentially maintain subsurface temperatures warm enough for liquid water, not at the surface, which would be frozen solid, but deep beneath the surface, in subsurface oceans kept liquid by the combination of internal heat and the insulating weight of thousands of kilometers of ice and rock above. Yet another mystery emerged from this line of reasoning. If subsurface liquid water can exist on a rogue planet, a world that has no star, that drifts in the coldest and darkest regions of the galaxy, then the requirements for habitability are even more relaxed than we thought. We already knew from the study of icy moons in our own solar system that life does not require direct sunlight. It requires liquid water, an energy source, and the right chemistry. If a rogue planet can provide all three, liquid water from radiogenic heat, energy from the same source, and the right chemical gradients from a rocky core interacting with that water, then the galactic habitable zone is not just the warm starlit neighborhood we usually imagine. It extends into the dark. It extends into the between stars, into the empty spaces where no light from any star has ever shone, into the drifting solitude of worlds that orbit nothing. Scientists soon discovered that detecting rogue planets is extraordinarily difficult. They emit no reflected starlight because there is no star to reflect. They glow only faintly in infrared from residual formation heat that fades over time. For the smallest rogue planets, even the most powerful telescopes struggle to detect them at all. The most successful technique for finding them has been gravitational microlensing, watching what happens when a rogue planet passes in front of a distant background star. The planet's gravity bends and briefly brightens the star's light in a characteristic way, revealing the planet's presence, even though we cannot see the planet itself. Microlensing surveys have suggested that rogue planets may be extraordinarily common. Some estimates suggest there could be several rogue planets for every star in the galaxy, meaning that the total number of free-floating worlds may be in the hundreds of billions, or even trillions. Hundreds of billions of worlds, drifting in silence, without sun, without season, without anything we typically associate with the sky. But perhaps not without something stranger, warmer, and more alive than we expect. And this is where things become even more fascinating, because the recent detection of GMBOs in the Orion Nebula has opened a question that no one expected to be asking so soon. Are rogue planets a common endpoint of planetary system formation? Or are they a common product of early stellar evolution in crowded, chaotic, star-forming environments. If the latter, if rogue planets are routinely born in places like the Orion Nebula, formed by the same processes that make stars, then the galaxy may have been seeding the darkness with free-floating worlds since the very first stellar nurseries began, collapsing billions of years ago. The universe has been making planets in the dark, quietly, without anyone watching, for almost as long as it has existed. We are only now beginning to count them. Of all the categories of exoplanets discovered in the last 3 decades, one stands out for its strange relationship to Earth, not because it is the most alien, but because it is almost familiar. Super-Earths. The name is simple and slightly misleading. A super-Earth is any rocky planet larger than Earth, but smaller than Neptune, typically defined as planets between 1.2 and 10 times the mass of Earth, with radii between 1.2 and 2 times Earth's radius. They are, in a sense, scaled-up versions of our world. But scaled-up version of our world turns out to be a much stranger thing than it sounds. On a super-Earth, with twice Earth's radius and perhaps 5 times its mass, the surface gravity would be significantly stronger. Not catastrophically so, perhaps 1.5 to 2 times Earth's gravity, but enough to have profound effects on everything from weather systems to mountain heights to the biology of any creatures that might live there. On a super-Earth with twice the gravity, trees cannot grow tall. The structural requirements of vertical growth against stronger gravity demand thicker trunks, shorter profiles, broader bases. Mountains cannot reach the heights of Everest. Stronger gravity pulls them down faster. Weather systems behave differently. Even the way continents move, the tectonics of the planet, is altered by the greater gravitational compression of the interior. Everything is heavier. Everything is shorter. Everything is denser. And yet, and here is what makes this fascinating, some super-Earths may be among the most geologically active, most volcanically vibrant, most chemically productive worlds in the galaxy. More mass means a larger, hotter interior. A larger, hotter interior means more radiogenic heating, more convection, more vigorous mantle activity. More mantle activity means more volcanism, more outgassing, more continuous replenishment of the atmosphere with the gases that life, as we understand it, requires. One of the most studied super-Earths is Kepler 442b, a planet about 1.3 times the size of Earth, orbiting a star some 1,200 light-years away. It sits comfortably within the habitable zone of its star, receives a similar amount of stellar energy to Earth, and has a mass that places it squarely in the super-Earth category. It is one of the highest-rated planets on various scientific habitability indices, not because we know it has life, but because its properties are consistent with the conditions life requires. But that wasn't the strangest part. The strangest part is a category of super-Earths that should not be habitable at all, and yet represent, according to some researchers, potentially the best environments for life in the entire galaxy. These are called super-Earths, orbiting red dwarf stars. Red dwarfs, also called M-dwarfs, are the smallest, coolest, and most common type of star in the galaxy. They account for approximately 70 to 75% of all stars. They are dim, long-lived, and unlike our sun, they can burn stably for not billions, but trillions of years. Our own sun has a lifespan of about 10 billion years. A typical red dwarf may burn for 10 trillion years, 1,000 times longer. If life needs time to evolve, red dwarfs are extraordinarily generous with it, and super-Earths around red dwarfs are common. The TRAP-PIST-1 system, perhaps the most famous exoplanetary system ever discovered, orbits a red dwarf star just 40 light-years from Earth. It contains at least 7 Earth-sized planets, at least 3 of which orbit within the habitable zone. At least 2 of those 3 have masses consistent with rocky, potentially water-bearing worlds. When scientists first discovered the full architecture of the TRAP-PIST-1 system in 2017, it caused something approaching a sensation in the scientific community. 7 Earth-sized worlds around a single star, 3 in the habitable zone, at a distance that the James Webb Space Telescope can actually study in detail. The answer raised an even bigger question, however. Red dwarf stars, for all their longevity and generosity with planets, have a significant problem. They are prone to violent stellar flares, eruptions of ultraviolet and X-ray radiation far more intense, relative to their host star's size, than anything our sun produces. And because the habitable zones of red dwarfs are very close to the star, meaning planets must orbit tightly to receive enough warmth, those planets are exposed to these flares at close range. The potential consequences for a planet's atmosphere are severe. Intense UV radiation can drive atmospheric escape, stripping the outer layers of a thin atmosphere over geological timescales. It can also destroy surface-level organic chemistry. On Earth, our ozone layer protects us from UV, but the ozone layer itself is sensitive to the kind of radiation that red dwarf flares produce. Whether a planet around a red dwarf can maintain a thick enough atmosphere to protect its surface, whether that atmosphere can regenerate through volcanic outgassing faster than it is stripped by stellar radiation, is one of the most debated questions in exoplanet science today. The James Webb Space Telescope has been observing the TRAP-PIST-1 planets with particular intensity. In 2023, it published results on TRAP-PIST-1b and TRAP-PIST-1c, the 2 innermost planets, which orbit inside or near the inner edge of the habitable zone. The results were sobering. Neither planet appears to have a thick CO2 atmosphere of the type that Venus has, suggesting that their atmospheres may be thinner than expected or substantially different in composition. But TRAP-PIST-1e, F, and G, farther out, deeper in the habitable zone, remain untested at the level of detail needed to characterize their atmospheres. The data is coming, slowly, observation by observation. The picture is being built. Scientists soon discovered that super-Earths may also exist in a fascinating compositional gray zone between rocky super-Earths, essentially giant versions of Earth or Mars, with solid surfaces, and ocean worlds. There is a transitional class of planets, sometimes called water worlds or Haitian planets. A Haitian world, hydrogen plus ocean, is a planet with a thick hydrogen-rich atmosphere above a global ocean. This combination, proposed by Cambridge researcher Niku Madhusudan and colleagues, could expand the habitable zone considerably. Hydrogen is an excellent greenhouse gas, warming a planet's surface even when it is farther from its star than Earth is from the Sun. K2-18b is the most famous candidate. It orbits a red dwarf about 124 light-years from Earth, and initial analysis suggested it might be a water-rich world with a hydrogen atmosphere. In 2023, James Webb observations detected tentative evidence of dimethyl sulfide, a molecule on Earth produced exclusively by living organisms, specifically marine microbes. In K2-18b's atmosphere, the scientific community was careful. Tentative means something specific in science. It means the signal is there, but not yet strong enough to exclude other explanations. The researchers were clear. This was not confirmation of life. It was a hint, a nudge, a signal pointing in a direction that demands further investigation. But the possibility sat in the data, quietly, refusing to go away. And this is where things become even more fascinating. Because if a Hycean world can produce biosignatures detectable from 124 light-years away, if the chemistry of living organisms in a global ocean under a thick hydrogen atmosphere creates molecular signatures that drift into the upper atmosphere and can be detected by a telescope in orbit around Earth, then we may already have the tools we need to detect life beyond our solar system. We may not need to travel to these worlds. We may only need to watch. There is a category of world that sounds, when you first encounter it, like something from a fairy tale, a planet made of diamond, not metaphorically, not decoratively. A world in which the interior, the deep geology that on Earth is made of iron and silicate rock, is instead composed, in significant part, of solid diamond, hundreds of kilometers of it, perhaps thousands. This is not pure fantasy. It is a prediction derived from real planetary science. The key is carbon. On Earth, carbon makes up a small fraction of our planet's overall composition. The Earth-Sun system has a carbon-to-oxygen ratio of roughly 0.5, meaning there is about half as much carbon as oxygen in the mix of elements available during planetary formation. Under these conditions, carbon tends to form compounds with oxygen, carbon dioxide, the minerals of limestone and dolomite. Carbon does not dominate the geology. It participates in it quietly in the background. But in other parts of the galaxy, around stars with different elemental compositions, the ratio of carbon to oxygen can be much higher. Some stars, particularly certain metal-rich stars, have carbon-to-oxygen ratios that approach or exceed 1. In these systems, oxygen is scarce enough that carbon cannot all bind to it. The excess carbon remains available to form other compounds. And at the pressures found deep inside a rocky planet, carbon under high pressure does not form soft graphite. It forms diamond. A planet forming around a carbon-rich star with the right mass and internal pressure profile could have a mantle composed primarily of diamond sitting beneath a crust of graphite, with a core potentially made of iron carbide rather than the iron-nickel mixture at Earth's center. Scientists soon discovered that one of the most studied candidates for a carbon planet is 55 Cancri-E, the same lava world we visited in the first section of our journey. Early analyses of 55 Cancri-E's mass and radius suggested that its density was consistent with a carbon-rich interior, possibly including a diamond layer beneath the surface. Later observations complicated this picture, suggesting that a more traditional silicate composition might also fit the data. Carbon planets remain a theoretical category more than a confirmed observational one. But the physics is sound, the chemistry is plausible, and the numbers work. And if they exist, if diamond planets are out there, orbiting carbon-rich stars, they would be among the most geologically alien environments imaginable. Diamond is an extraordinary material. It is the hardest natural substance known. It conducts heat with extraordinary efficiency, far better than copper or silver. It is electrically insulating, and it is chemically almost completely inert. It does not react with most substances at typical planetary surface conditions. A planet with a diamond mantle would therefore behave very differently from Earth. On Earth, the slow convection of molten silicate rock in the mantle drives plate tectonics, the process by which Earth's crust is continuously recycled, pulling carbon into the deep interior and releasing it through volcanic activity, regulating the greenhouse effect and maintaining climate stability over geological timescales. On a diamond planet, mantle convection might work very differently, or not at all. Diamond is viscous at the pressures and temperatures found in a planetary mantle, but it may not convect in the same way as silicate rock, potentially resulting in a planet without plate tectonics as we know it. Without plate tectonics, a planet's ability to regulate its long-term climate may be severely compromised. On Earth, plate tectonics helps draw excess carbon dioxide out of the atmosphere through the subduction of carbonates, maintaining temperatures within the range where liquid water can persist. Without this mechanism, carbon dioxide could accumulate, driving a runaway greenhouse effect. But that wasn't the strangest part. The strangest part of carbon worlds is what their surfaces might look like. A planet with a carbon-rich crust would have rocks made of graphite and silicon carbide rather than the silicates that form granite, basalt, and sandstone on Earth. Its mountains would be dark, the color of graphite, not the grays and browns of terrestrial stone. Its sand would be black. Its beaches, if it had oceans, would be shores of dark crystalline carbon, lapping against whatever fluid occupied its seas. And what fluid might that be? Water, if present in a carbon world, might not behave as it does on Earth. Carbon can form compounds with water in ways that could change the surface chemistry profoundly. Some models suggest that the oceans of a carbon world, if they exist, might be oceans of liquid carbon compounds, TARs, hydrocarbons, exotic solutions of dissolved carbon chemistry, rather than the clean water oceans of Earth. Yet another mystery emerged when researchers began thinking about biology on such a world. Life on Earth is carbon-based. Our molecules, DNA, proteins, lipids, carbohydrates, are built on carbon backbones. Carbon's ability to form 4 stable bonds simultaneously, creating complex, 3-dimensional molecules of almost unlimited variety, is what makes it ideal as the basis of biological chemistry. On a carbon-rich world, carbon is not rare. It is everywhere. The rocks are made of it. The atmosphere might be thick with carbon compounds. The surface might be coated in organic material. This could be an extraordinary advantage for life. A world where the basic building blocks of biology are not scarce commodities, but environmental constants embedded in the geology itself. Or it could be a disadvantage. Some forms of carbon chemistry are poisonous to the reactions that Earth life relies on, and a world where carbon is everywhere might not provide the chemical gradients and interfaces. The boundaries between carbon-rich and carbon-poor zones that are thought to be important for the emergence of self-replicating chemistry. Scientists soon discovered that this question is genuinely open. We have no confirmed carbon planets. We have no biology to compare against. We have only models, and the models do not yet agree. But here is what makes all of this worth thinking about carefully. The periodic table does not change from star to star. The elements are the same everywhere in the universe. What changes is the ratio in which they appear, determined by the history of nucleosynthesis, the process by which atomic nuclei are built inside stars and scattered across the galaxy when those stars die. Different stellar populations in different parts of the galaxy, with different histories of star formation and supernovae, have different elemental abundances. The inner galaxy has more heavy elements. Some regions are richer in carbon, others in oxygen, others in nitrogen or sulfur. The geology of a planet, and by extension, its habitability, its chemistry, its potential for life, is downstream of this cosmic history. Every planet is a record of the stars that came before it. Every world, no matter how alien, carries in its rocks the fingerprints of long-dead suns. There is a line on some planets where everything changes. Not a metaphorical line, not a political boundary or a geographical feature, a real physical line that encircles the planet. A boundary between two worlds that exist simultaneously on the same sphere. On one side, eternal day, a sun that never sets, a sky that never darkens, light so constant that no shadow ever falls at the same angle twice. On the other side, eternal night, a sun that never rises, a sky perpetually thick with stars, a cold so deep and so permanent that the atmosphere itself may freeze and fall to the ground. The line between them is called the terminator, the boundary between permanent day and permanent night on a tidally locked planet. Tidal locking is a gravitational phenomenon that occurs when a planet orbits close enough to its star that the gravitational interaction between the two bodies slows the planet's rotation until it matches its orbital period. The Moon is tidally locked to Earth, which is why we always see the same face of the Moon from our planet's surface. The Moon takes about 27 days to orbit Earth and about 27 days to rotate once on its axis. These are the same number because tidal locking made them so. For exoplanets orbiting close to their stars, and particularly for planets in the habitable zones of red dwarf stars, which lie very close to those dim, cool stars, tidal locking is not a curiosity. It is an expected condition. Many of the most promising, potentially habitable exoplanets are almost certainly tidally locked. This creates a planetary environment that has no parallel in our solar system. Imagine a world where the sun hangs motionless in the sky, directly overhead at a single point on the surface, the substellar point, and spreads its heat and light outward from that fixed center. The rock directly beneath the substellar point would be seared by continuous, unrelenting stellar radiation. Temperatures there might climb to hundreds or even thousands of degrees Celsius, depending on the star and the distance. As you move away from that central point toward the terminator, temperatures drop. The star appears lower in the sky, a flattened ellipse near the horizon, eventually just grazing the edge of the world. Temperatures at the terminator might be moderate, warm on the day side, cool on the night side. And on the night side, temperatures plummet. Without any stellar heating, the surface would radiate its own heat away into space, losing energy continuously to the cold of the interstellar void. The night side of a tidally locked planet could be extraordinarily cold, cold enough that even carbon dioxide, which makes up a large fraction of many planetary atmospheres, would condense out and freeze onto the surface. This creates what scientists call an atmospheric collapse scenario, in which the cold night side acts as a giant cold trap, pulling the atmosphere off the day side and freezing it out, until the planet's entire atmosphere is locked onto the night side as a thin layer of frost. Whether this happens, and how catastrophic it is for habitability, depends crucially on one thing: the atmosphere's ability to transport heat from the day side to the night side. Scientists soon discovered that the fate of a tidally locked world depends almost entirely on atmospheric dynamics. If the atmosphere is thick enough, and if the greenhouse properties of the atmospheric gases are strong enough, heat transported by winds from the permanent day side can warm the night side sufficiently to prevent atmospheric collapse. The planet settles into a state of extreme but sustained asymmetry, hot on one side, cold on the other, with a turbulent, storm-lashed terminator zone between them. And it is in that terminator zone, the permanent twilight belt that circles the planet from pole to pole, that something potentially extraordinary may happen. Temperatures at the terminator can be moderate, not scorching, not freezing, but somewhere in between. Liquid water, if it exists on such a planet, might persist at the terminator more easily than anywhere else on the surface. The constant availability of light, diffuse, grazing light from the sun perpetually at the horizon, could potentially drive photosynthesis, and the atmospheric dynamics at the terminator would be uniquely complex. Warm, moist air rising from the day side meets cold, dry air descending from the night side. The collision creates weather. Perpetual weather, locked in place, always occurring at the same latitude, on the same longitude. Persistent storms, constant cloud systems, a weather pattern that never changes, but never stops. For any life in the terminator zone, the sky would always look the same. The sun would always be at the horizon. The clouds would always be in the same formations. And yet the world would be alive with constant wind, constant moisture, constant meteorological activity. But that wasn't the strangest part. The strangest part is what happens to the night side, on the coldest parts of the night side if the atmosphere can maintain itself against collapse. Temperatures might be cold enough for exotic ice chemistry, carbon dioxide snow, nitrogen, ice plains, methane frost in craters and valleys, a world of frozen quiet, far from the light, possibly harboring subsurface liquid water warmed by the planet's internal heat. And in between the frozen night side and the scorching day side, running along the terminator like a permanent scar across the planet's face. A belt of perpetual twilight where the most complex and potentially the most habitable conditions might exist. The TRAP-PIST-1 planets are the best studied examples of potential terminator worlds. All 7 of them are almost certainly tidally locked to their star, given their tight orbital periods. TRAP, PIST, 1E, the planet considered most likely to be habitable in that system, orbits in about 6.1 Earth days. For the inhabitants of TRAP, PIST, 1E if there are any, a year lasts 6 days. The sun never moves. The terminator never shifts. Time is not measured in sunrises or sunsets, in the turning of seasons or the shortening of days. Time there would have to be measured by something else. The cycles of weather, the tides, the gravitational pull of neighboring planets, all close enough to exert significant tidal forces. The slow drift of the TRAP-PIST, one star's faint red light across the sky as seen from the poles. A tidally locked world imposes a radically different relationship between a planet and time itself. What happened next surprised researchers who modeled the climate of tidally locked planets in the habitable zone. The models initially suggested that the atmospheric dynamics required to prevent collapse and maintain a livable environment might be unstable. That small perturbations in orbital parameters or atmospheric composition could push a tidally locked planet into runaway states, either too hot or too cold. The Goldilocks window, already narrow for conventional planets, seemed vanishingly thin for tidally locked ones. But more sophisticated models, incorporating clouds, their chemistry, their reflectivity, and their ability to regulate surface temperature, produced a more encouraging picture. Clouds, it turns out, may save tidally locked planets. On the permanent day side, intense heating drives vigorous convection, which generates thick clouds. And thick clouds reflect incoming stellar radiation back into space, moderating the surface temperature. The planet self-regulates through cloud formation in ways that simple models missed. The universe, once again, is cleverer than our first models assumed. We have journeyed across a vast range of alien environments, lava worlds and ocean worlds, hot Jupiters raining glass and iron, rogue planets drifting in the dark, super-Earths with heavy skies, tidally locked worlds split between eternal fire and eternal ice. And now we arrive at the question that underlies all of the others. Could any of these worlds be alive? Not alive in a vague poetic sense, alive in the specific biochemical sense, hosting organisms that metabolize, reproduce, evolve. Life is a physical and chemical process inscribed in molecules, powered by energy gradients, maintaining itself against the tendency of the universe to dissolve complexity into chaos. The search for that kind of life on exoplanets is one of the most technically demanding scientific endeavors ever attempted. We cannot go there. We cannot send a probe. The nearest potentially habitable exoplanet systems are years away at the speed of light, and we have no spacecraft capable of anything close to that velocity. What we can do is read the air. When starlight passes through a planet's atmosphere, whether during a transit, when the planet crosses in front of its star, or via other techniques, the molecules in that atmosphere absorb specific wavelengths of light. Different molecules absorb different wavelengths with unique precision, leaving fingerprints in the spectrum of light that reaches our telescopes. These fingerprints are called absorption features. They are as distinctive as the spectral lines of individual elements, and they can, in principle, reveal the presence of specific molecules in a distant planet's atmosphere from trillions of kilometers away. The molecules scientists are searching for fall into several categories. The first are what might be called simple habitability markers: water vapor, carbon dioxide, methane. These do not prove life exists. They are common products of geological and atmospheric chemistry, but their presence, in the right proportions, suggests a world whose basic chemistry is compatible with the kind of processes that, on Earth, eventually led to life. The second category is what researchers call disequilibrium biosignatures. The idea here is powerful in its elegance. On a planet without life, chemistry tends toward equilibrium. Reactive molecules react with each other and form stable end products. Oxygen and methane, for example, react with each other. They destroy each other in chemical reactions driven by sunlight. In a purely geological atmosphere, you would not expect to find both oxygen and methane in significant quantities simultaneously. One or the other would dominate. But on Earth, both oxygen and methane are present in the atmosphere. Why? Because life is continuously producing both. Photosynthetic organisms pump oxygen into the atmosphere. Methanogenic microbes pump methane. The biological production of both gases outpaces the chemical destruction of both, maintaining a state of chemical disequilibrium that persists as long as life persists. If we find a planet whose atmosphere contains gases in combinations that chemistry alone would rapidly destroy, combinations that can only be sustained by ongoing biological production, that would be a powerful signal. Scientists soon discovered, however, that disequilibrium is not a perfect indicator. Volcanic activity can produce gases that mimic biological disequilibrium. Certain photochemical reactions, driven by ultraviolet light from the host star, can also create unexpected molecular combinations. The universe is full of non-biological processes that produce complex, sometimes surprising chemistry. This is why researchers speak of biosignatures in terms of probability, not certainty. Finding oxygen alone in an atmosphere is not strong evidence of life. There are non-biological ways to produce atmospheric oxygen. Finding oxygen plus methane is more suggestive. Finding oxygen plus methane plus nitrous oxide plus water vapor in specific proportions begins to look very much like a biosphere. The answer raised an even bigger question. What if life elsewhere in the galaxy uses chemistry we have not imagined? The biochemistry of life on Earth uses a specific set of molecules, the 20 amino acids that build proteins, 4 nucleotides that encode DNA, lipids that form cell membranes. But these are not the only possible biochemistries. There is no law of physics that demands life use these specific molecules. Life based on different amino acids, non-canonical ones, not found in Earth biology, could potentially produce different biosignature gases. Life using entirely different metabolic pathways might produce molecules we have not thought to look for. Life in a radically different solvent, not water, but liquid ammonia or liquid methane, as proposed for potential life in Titan's hydrocarbon lakes, would produce a completely different chemical fingerprint. We are searching for life like ours. We may be blind to life that is not. Yet another mystery emerged from the study of biosignatures that is both humbling and fascinating. Even if we detect a strong biosignature, even if we find a planet whose atmosphere cannot be explained without invoking life, we will face a profound interpretive challenge. We will have evidence that something biological is happening, but we will have no idea what that biology looks like. Is it microbial? Is it complex? Is it intelligent? Is it microscopic films of chemistry on the underside of ice? Or is it forests, oceans, full of creatures, civilizations? A biosignature in an atmosphere tells us that life is present, or was recently present. It tells us almost nothing about the nature of that life. We would know someone is home. We would not know who. What happened next in the history of biosignature science was the launch of the James Webb Space Telescope in December 2021 and its first science observations in 2022. Webb is the first telescope with the sensitivity and wavelength coverage to actually attempt atmospheric characterization of habitable zone planets around nearby stars, particularly the TRAP-PIST-1 system. The observations are ongoing. They require years of accumulated data, dozens of transits observed, dozens of spectra accumulated, and combined to build up the signal-to-noise ratio needed to detect faint atmospheric features. But the machinery is in motion. The telescope is watching. The data is accumulating. And somewhere in the spectrum of starlight passing through the atmosphere of TRAP-PIST-1E or GJ1214b or K2, 18b or one of the hundreds of other worlds being studied, the answer may already be there, waiting in the data, not yet assembled into a picture we can recognize. We are not looking at alien worlds as a passive exercise in wonder. We are actively searching, with real instruments, for real life. The search has begun in earnest, and this is where things become even more fascinating. Because the greatest discovery in the history of science, if it comes, may arrive not as a dramatic announcement, but as a quiet, statistical accumulation of data points that slowly, undeniably, converge on a single conclusion. Life is not unique to Earth. We have been building toward this, through lava and iron rain, through endless oceans and frozen twilight, through rogue planets in the dark and diamond geology, and the chemical fingerprints of distant atmospheres. We have been moving steadily toward the worlds that raise the most profound question of all, the worlds that look like home, the habitable zone, sometimes called the Goldilocks zone, because it is not too hot and not too cold, but just right for liquid water to exist on a planetary surface. Is not a single place. It is a range of orbital distances from a star, varying depending on the star's luminosity and the planet's own properties. For our Sun, the habitable zone extends roughly from the orbit of Venus to the orbit of Mars, with Earth sitting comfortably in the middle. For smaller, cooler red dwarf stars, the habitable zone is much closer. Planets in the habitable zone of a red dwarf orbit their star in days or weeks, not years. For larger, hotter stars, the habitable zone extends farther out. Planets might need to orbit at distances greater than Earth's to stay cool enough. As of mid-2025, we have identified dozens of planets in the habitable zones of their stars, with more being added to the list every year. A handful of these are rocky, or at least consistent with being rocky, based on their size and density. And a few of these rocky habitable zone planets orbit stars close enough to Earth that the James Webb Space Telescope can attempt to characterize their atmospheres. These are the candidates, the short list, the worlds that keep astronomers up at night. Proxima Centauri b is perhaps the most discussed. It orbits Proxima Centauri, the nearest star to the Sun, at just 4.24 light-years away, in about 11.2 Earth days. It was confirmed in 2016 and remains a subject of intense interest. Its mass is at least 1.07 times Earth's mass, suggesting a rocky planet. It sits within Proxima Centauri's habitable zone. But Proxima Centauri is a red dwarf, and a particularly active one. It flares frequently, and whether Proxima Centauri b retains any atmosphere, given this flare activity, is a major open question. Some models suggest a rocky, airless world, a second Mars. Others suggest that a thick enough initial atmosphere, replenished by volcanic outgassing, might survive the flare environment. We do not know, at 4.24 light-years, the nearest possible neighbor. We cannot yet answer the question directly. Scientists soon discovered that the picture becomes more complex and more interesting as we look at more distant systems. Teegarden's star, B and C, two planets orbiting a small red dwarf just 12.5 light-years away. Both orbit within the habitable zone and have masses consistent with rocky planets. On planetary habitability indices, Teegarden's star B scores extraordinarily high. Some analyses place it among the most Earth-like planets ever found, based on the combination of stellar irradiation, estimated size, and orbital parameters. GJ 667 cc orbits a star about 22 light-years away, and also sits in a temperate orbit. Kepler 442b, as mentioned earlier, at about 1,200 light-years, is one of the best-studied large habitable zone candidates. Kepler 452b, dubbed Earth's cousin when it was discovered in 2015, orbits a sun-like star at a distance similar to Earth's orbital distance. It is somewhat larger than Earth, at about 1.6 times Earth's radius, placing it in the ambiguous zone between super-Earth and mini-Neptune. But the most famous and most observed candidates are the TRAP, PIST, planets, specifically TRAP-PIST, 1, D, E, F, and G, all of which orbit within or near the habitable zone of their red dwarf host. Of these, TRAP-PIST, 1E is considered by many planetary scientists to be the single most promising candidate for a habitable world currently known. It receives slightly less stellar energy than Earth receives from the Sun, about 66%, placing it in a temperate zone. Its mass is estimated at about 0.77 times Earth's mass, suggesting it could be a rocky planet with a surface. Its orbital period is about 6.1 days, and it is close enough, at just 40 light-years, that Webb can study it, that it is studying it right now, orbit by orbit, transit by transit, slowly building up the spectral data that will eventually tell us whether this world has an atmosphere and what that atmosphere contains. Yet another mystery emerged in the study of TRAP-PIST, one from an unexpected direction. The TRAP-PIST, 1 planets orbit very close to each other. Their gravitational interactions are measurable. They slightly perturb each other's orbits in ways that reveal their masses with unusual precision. And those mass measurements show something intriguing. The TRAP-PIST, 1 planets are all slightly less dense than Earth. This suggests they may contain more water by mass fraction than Earth does. They may be water-rich worlds, not necessarily covered in global oceans like GJ 1214b, but perhaps with more abundant water distributed through the rock, or in surface oceans that are somewhat shallower than a pure water world, but deeper than Earth's. Water-rich, rocky worlds in the habitable zone, orbiting a star that will live for trillions of years, 40 light-years away, close enough to study with our existing instruments. If the history of life on Earth teaches us anything, it is that once the conditions for life are in place, life tends to appear. Earth formed about 4.5 billion years ago. The oldest evidence for life on Earth dates to around 3.5 to 4 billion years ago. Life appeared within the first 100 million to billion years of Earth's existence, almost as soon as the surface cooled enough for liquid water to persist. If the TRAP-PIST-1 planets have liquid water on their surfaces, and if the chemistry of rock and water and energy that seems to be so productive on Earth is doing its work there, then life has had not just billions, but potentially trillions of years to emerge and evolve. What would trillions of years of evolution produce? We genuinely do not know. We have no model for biological complexity on timescales that dwarf Earth's entire history by factors of hundreds or thousands. The answer to that question may be the most important thing humanity ever learns, and we are right now, trying to find it. Every world we have visited on this journey has taught us something. The lava worlds taught us that geological violence and chemical complexity are not opposites. They can be partners in creating the conditions from which stability and, perhaps, life eventually emerge. The ocean worlds taught us that liquid water is not a fragile exception in the universe. It is everywhere. It persists under ice, under pressure, in the dark, warmed by the heat of interiors that no sunlight will ever reach. The hot Jupiters taught us that planets do not stay where they form. The cosmos is dynamic. Systems evolve. And in that evolution, the chemistry of worlds changes in ways that challenge every model we build. The rogue planets taught us that a world does not need a star. Warmth comes from the inside too. And the inside of a planet lasts longer than most stars. The super-Earths taught us that Earth is not the template for a habitable world. It is one example of many, and some of those other examples may be more geologically active, more chemically productive, more generously endowed with the raw materials of life than Earth itself. The diamond worlds taught us that geology is downstream of stellar chemistry, that the kind of planet you get depends entirely on what star you are born around, and that the universe has made stars with a bewildering variety of elemental compositions, implying a bewildering variety of planetary geologies we have barely begun to explore. The tidally locked worlds taught us that day and night are not universal concepts, that the relationship between a world and its star can be radically different from the one Earth has, and that even in the most extreme versions of that relationship, life might find the twilight boundary and make something of it. The biosignature hunt taught us that we are already searching, not passively wondering, actively searching, with instruments of extraordinary sensitivity for the chemical fingerprints of life in the atmospheres of worlds we cannot visit, and that the signals we find tentative, ambiguous, demanding years of verification, are already beginning to complicate the story of life's uniqueness. And the Goldilocks candidates taught us that the universe has been extraordinarily generous in placing rocky, water-rich, temperate worlds around the most common and longest-lived stars in the galaxy. What does all of this add up to? Scientists soon discovered that the emerging picture is not one of a universe indifferent to life. The universe is not actively friendly to life either. It is vast, violent, cold, full of radiation and collision and gravitational catastrophe. But the preconditions for life, liquid water, chemical complexity, geological activity, energy gradients, appear to be common, staggeringly common. The Fermi paradox, the question named after physicist Enrico Fermi, who asked something like, if the universe is so full of potentially habitable worlds, where is everybody? Looms over all of this. If life is common, if it emerges wherever conditions allow, if it has had billions and trillions of years to evolve in countless star systems across the galaxy, then where are the signals? Where are the civilizations? Why is the universe so quiet? This is not a question with a comfortable answer. The most optimistic interpretations suggest that we simply have not been looking long enough, at the right frequencies, with sufficient sensitivity, or in the right places. Our radio telescope searches for extraterrestrial intelligence. The SETI program covers only a tiny fraction of the galaxy at a narrow range of frequencies over a span of decades. The universe is very large, and we are very new at looking. The more sobering interpretations suggest that something, somewhere between the emergence of simple life and the emergence of technological civilization, is extraordinarily difficult. That while microbial life may be common, complex life may be rare. That while oceans full of microbes may occupy many of the worlds we have cataloged, civilizations capable of broadcasting radio signals into the galaxy might be extraordinarily rare, perhaps even unique. We do not know which interpretation is correct. We cannot know without the evidence that only ongoing observation and search can provide. But here is what the last 3 decades of exoplanet science have definitively established. We are not alone in the cosmos in the sense of being the only planet. The universe is full of planets, more planets than we could visit in any conceivable future, more worlds than we have names for, orbiting more stars than we can count, in a galaxy that is itself one of hundreds of billions. Whether we are alone in the biological sense, whether life has arisen elsewhere, whether any of those countless worlds have produced a chemistry of replication and metabolism, and evolution is a question we are actively working to answer with the best tools humanity has ever built. And the answer is close. Not in the sense of certainty, but in the sense of approach. We are approaching the moment when we will have enough data, enough sensitivity, enough understanding of atmospheric chemistry and planetary physics to make the first informed statement about whether life beyond Earth is real. That moment may come in decades. It may come in years. It may come when a telescope we have not yet built detects a combination of gases in the atmosphere of TRAP, PIST, 1e that can only be explained by biology. Or it may come sooner, in a dataset that already exists, in the spectrum of starlight through a distant atmosphere, waiting to be analyzed by a scientist who has not yet been born. The universe is not done speaking to us. We are only beginning to listen. Settle back now. The journey is not over. It will never be over, because the universe does not have an edge we can reach, or a final mystery we can close. But for a moment, let us simply be still and think about where we have been. We began standing on a glowing world where rock itself is a vapor in the sky. We traveled to oceans so deep that water becomes something new under pressure, something alien, something that no ocean on Earth has ever been. We drifted past worlds of iron rain and glass storms, and winds that move faster than any sound. We entered the dark between stars, where planets drift without purpose, without sun, without season, and possibly without the loneliness we would project onto them. We stood at the terminator line of a tidally locked world and watched a sun that would never move, frozen on the horizon of a planet whose day is also its year. We looked at the chemical fingerprints of atmospheres we cannot breathe, on worlds we cannot stand on, around stars that are not our sun. And we asked the question, quietly, carefully, without insisting on an answer, whether any of those atmospheres hold a secret we have been searching for since the first human being looked up at the night sky and wondered if they were alone. There is something profound about this moment of history that is easy to miss if you are too close to it. We are the first generation of human beings who know with certainty that planets beyond our solar system exist. The first who have seen, in the data, the outline of their atmospheres. The first to have actually confirmed, that the universe is not empty of worlds. It is full of them, more full than anyone imagined even 50 years ago. Every generation before ours looked at the night sky and could only guess. The stars were beautiful and distant, and perhaps they had companions. Perhaps there were other Earths, other suns, other places. But it was all hypothesis, all philosophy, all longing without evidence. We have evidence. 5,000 confirmed exoplanets, thousands more candidates, a telescope in space right now, this very moment, collecting the photons of starlight that have passed through the atmosphere of a world that orbits another star, measuring the chemistry of a sky we will never breathe. What we have done, as a species, in the span of 30 years, is astonishing. We went from 0 confirmed worlds beyond our solar system to a catalog of thousands. We built instruments sensitive enough to detect a planet by the wobble it induces in a star trillions of kilometers away. We designed a telescope that can analyze the chemical composition of an atmosphere on a world 40 light-years distant by watching how it modifies the spectrum of light from its star during a transit that lasts a few hours. We are small. We have always been small. But we are extraordinarily clever and extraordinarily curious, and in that curiosity, there is something that feels, and here the language becomes genuinely difficult, because the word is large, and we use it carefully. There is something that feels sacred, not in a religious sense, though many people find their own meaning in these questions, and that meaning is entirely their own, but sacred in the sense of deserving reverence, of being worthy of our full attention, of mattering in a way that transcends convenience or utility. The question of whether we are alone in the universe is not a question of academic interest. It is a question about the nature of existence itself. If we are alone, if Earth is the single living world in a cosmos of billions of galaxies, then the weight of that solitude is almost incomprehensible. Every creature that has ever lived, every consciousness that has ever formed, every thought, every feeling, every dream, concentrated on one small world, around one ordinary star, in one unremarkable arm of one galaxy among hundreds of billions. And if we are not alone, if life has found its way into the deep oceans of a water world, or into the twilight belt of a locked planet, or into the warm interior of a rogue drifting in the dark, then the universe is more generous, more creative, more astonishing than we have yet been able to imagine. Both possibilities are overwhelming. Both deserve the silence to sit with them. There is a kind of peace in not knowing the answer yet, in being at the threshold of the question, in looking out at the sky and understanding that every point of light may have worlds around it. Strange worlds, familiar worlds, dead worlds, living worlds. In that, we are just beginning to learn to read them. The universe has been here for 13.8 billion years. Life on Earth has been here for about 4 billion. Homo sapiens have existed for perhaps 300,000 years. We have had telescopes for about 400 years. We have had space telescopes for a few decades. We have known exoplanets exist for 30 years. In the timeline of the cosmos, we are newborns, just opening our eyes, just beginning to focus on the world around us, which turns out to be much larger, much stranger, and much more populated than anyone guessed. And yet here we are, small and new and curious, looking up. That looking matters. It may be the most important thing our species has ever done, not because it will immediately feed anyone or cure anything, but because in the act of looking out and asking what is there, we are doing something that no other process in the known universe does. We are the cosmos becoming aware of itself, asking about itself, wondering about itself, a universe that, for most of its history, simply existed, burning and cooling and expanding, forming stars and planets and black holes and galaxy clusters, all in silence, all without witness, has produced in us something that wonders at it. That wondering is not small. It is, in a profound sense, the most significant thing that has ever happened in 13 billion years of cosmic history. And tonight, in this quiet, in this stillness, you have been part of it. You have traveled to alien worlds and looked at them with the eyes of the species that, against all odds, in this small corner of an enormous galaxy, learned to ask the right questions. The stars are still there, every one of them burning, every one of them possibly, just possibly, with a world nearby. And on some of those worlds, perhaps something is also looking back across the same vast dark, asking the same impossible question. Take that with you into the night. Rest well. The universe will be there when you wake.